Hey everybody, welcome back. Today in this video, we're going to be skipping section 6.3. It's not really necessary, and we're going to go straight to 6.4, which is about a very important theorem called the Central Limit Theorem. So the Central Limit Theorem is an incredibly useful tool that allows us to use the normal distribution to approximate sample sizes that are beyond a certain size will follow a normal distribution. So it's actually really helpful. Okay, so in this section we introduce and apply the Central Limit Theorem. The Central Limit Theorem allows us to use a normal distribution for some very meaningful and important applications. Okay, so what is the Central Limit Theorem? The Central Limit Theorem says that if you have a sample of some size n, where n is greater than 30, the sampling distribution of your sample mean x bar, remember x bar is just the mean for your sample, so the average of all your data values, can be approximated by a normal distribution with mean mu and standard deviation sigma over the square root of n. So really, all that's new here is we are trying to find a sampling distribution for x bar, which is actually the sample mean. And it turns out that because of this central limit theorem, all we have to do is use the standard mean mu, but the standard deviation is a little bit different. So the standard deviation is actually going to be sigma over the square root of n, where n is our sample size. So it turns out that all the techniques we learned earlier in chapter 6 still apply here for the central limit theorem. The only new thing is just that instead of having a standard deviation of just sigma, we're going to be using a standard deviation of sigma divided by the square root of n. That's really the only new thing. Okay, now the thing about the central limit theorem is you have to be given a population, and it can be a population with any distribution, but that population has to have mean mu and standard deviation sigma. Okay? And then when you're selecting your samples, they have to be simple random samples, and they all have to be of size n, and they have to be selected from the population. But when you're doing your homework, quizzes, and exam, they're already going to satisfy these conditions. So this slide probably isn't going to be particularly helpful. It's just here for your education about it, really. Okay, so the requirements for using the central limit theorem is just that you have a population that either has a normal distribution or, as we said, the sample sizes have to be greater than 30. So remember that greater than doesn't include 30. So that means you have to have a sample size of at least 31 data values or more. Otherwise, you have to know that if you have less than or equal to 30, your population has to have a normal distribution. Okay. So, like I said, we are trying to apply applications from the real world to the distribution of our sample mean x bar. And it turns out that because of the central limit theorem, the mean of all the values of x bar is just mu x bar, which is equal to mu. And then the only thing that's new here is the standard deviation of all values of x bar is going to be sigma sub x bar, which is just sigma over the square root of n. So you end up having to divide by square root of n for your sigma, but that's really the only new thing that we're doing here. So recall the z-score formula that we've seen multiple times in this course. So the z-score conversion for x bar is just the same formula we've been dealing with. It's just we have a square root of n in the bottom here. So z equals x bar minus mu all over the standard deviation. Here, the standard deviation for x bar is actually going to be sigma over the square root of n. So really, if you look at this z-score formula, it's just the same z-score formula that we've always been using, with the exception of this square root of n. Everything else is identical to the z-score formula we were using before. It's just instead of applying to a data value x, we're talking about the sample mean x bar. Okay, and that ends up meaning that you have to divide by the square root of n. Okay, so the book makes it seem pretty complicated, but it's actually not that bad. It's really just stuff that we've been doing already. So when you're doing your homework and quizzes from this section, you may find them to be pretty straightforward because the only new thing is that you're dividing by the square root of n when you're using the z-score formula. But that's not too incredibly difficult to do on a calculator. And then the only thing to notice is that for this central limit theorem to work, you either need to have the original population be normally distributed, or you need to have n, which is the number of data values, n has to be greater than 30. If it's not normally distributed and n is less than or equal to 30, in that case, the distribution of the sample mean x bar cannot be approximated by a normal distribution, and the methods of this section do not apply. Okay, but that's, again, not going to be particularly helpful for the homework quizzes and exam, because all of the problems there are problems that you can apply the central limit theorem to. Okay. All right. So if you're using the central limit theorem in the real world, all you have to check is that either the original population has a normal distribution or the sample size is n, and n has to be greater than 30. Okay, and then as long as those requirements are met, then you need to decide whether you're either going to be looking at an individual value or looking at the sample mean x bar. So if it's just an individual value, that's actually the process that we did in section 6.2 from this chapter. So make sure you watch that, the videos from that section. But if you just have a single value x, that's what we did in 6.2. So for an individual value, you would just use, in your homework, you're just going to use the standard z-score formula. So z equals x minus mu over sigma. But what's new here is if we're not just talking about a single value x, we're talking about the sample mean x bar, that's when we use this new formula, which isn't really that new of a formula. It's still z equals x minus mu over sigma. It's just here, instead of x, we have an x bar, which is standing in for x in a way. And then down here, instead of sigma, we have sigma over the square root of n. Okay, so the only thing that's tricky is you just need to read the problem. If they're talking about the normal distribution of a single value x, then you would just use the usual z-score formula. But if we're talking about the sample mean x bar, we use this formula. Okay, so that's hopefully not too bad. All right. All right, and then this is also a lot of theoretical stuff in our slides. But if all possible simple random samples of size n are selected from a population with mean mu and standard deviation sigma, the mean is going to be denoted by mu sub x bar, and the standard deviation of all sample means is denoted by sigma sub x bar. But like I said, we're using the same mu that we used to. The only difference is sigma now we have to divide by square root of n. Okay. All right. So let's jump into an example. Because we've seen lots of examples before in earlier sections, we're just going to do this one example, which really has two parts for this lecture. Okay, so first off, let's read the problem. American Airlines uses Boeing 737 jets with 126 seats in the main cabin. In an attempt to create more room, an engineer is considering a reduction of the seat width from 16.6 inches to 16.0 inches. Adult males have hip widths that are normally distributed with a mean of 14.3 inches and a standard deviation of 0.9 inches. So just remember that the mean that they're talking about here and the standard deviation that they're talking about is, this mean is the population mean, so this is going to be mu. Okay, so out of this, I already know that mu equals 14.3 inches, and then sigma is 0.9 inches. And it's helpful to just write down the numbers, and that way we can plug them into the formula. All right, and then when we actually look at the problem, it has multiple parts. So in part A, they want us to find the probability that a randomly selected adult male has a hip width greater than the seat width of 16.0 inches. So I want you to think about this. Does this say, do you think this is talking about the sample mean, or do you think this is talking about an individual data value x? You can pause the video if you need to. And of course the answer is, because we're just talking about one randomly selected adult male, here all we have to do is use the standard z-score formula, the one that we learned in 6.2. Okay, the only thing to be careful for is, remember, when it says greater than goes to the right. So for part A, what they really want us to do is find the probability that x is greater than 16.0. Now, why am I writing x and not x bar? Well, they're not saying anything about a sample mean. They're just talking about for one adult male. So that's just x. In part B, they're going to be talking about 126 cabin seats. And then, so that's where we would be using the central limit theorem. But part A, we don't even have to use the central limit theorem. We can just use the standard z-score formula. Okay, so let's go ahead and do that. All right, so just like in 6.2, we have to convert this x score into a z-score by using the z-score formula. So because we're just estimating, or not estimating, but converting x to a z-score, we don't have to divide by the square root of n. So it's just going to be, to convert it to a z-score, we're going to use the formula x minus mu over sigma. Okay, so plugging in, that's going to be Here x is 16. So 16.0 minus mu, which is 14.3, all over sigma, which is 0.9. Okay, and then most people would use a calculator. Unless you're good at doing math on decimals in your head, a calculator is usually quicker. So here, if we do 16.0 minus 14.3, that gives us 1.7. Okay, so our numerator is 1.7, our denominator is 0.9. Okay, and then 1.7 divided by 0.9 gives us a z-score of 1.8 repeating, which is, remember you're supposed to round z-scores to 2 decimal places. So this is going to round up to 1.89. Right, so really what we're trying to find here is the probability that z is greater than 1.89. So this is just straight out of section 6.2. So if you're a little bit lost here, make sure you watch or re-watch the video from 6.2 because we go over all the cases. Now, in order to use table A2, recall that greater than goes to the right. So we're looking at the area to the right here. But table A2 indicates the area to the left of a z-score. So for the area to the right, we have to use the formula, which is, it's going to be 1 minus the area in table A2. Okay, so that's all. That should all be pretty obvious to you, though, from if you've watched my other video. Okay, so if we look up z equals 1.89 in table A2, let's see what area we get. So the picture here is x is 16.0, mu is 14.3, sigma is 0.9, and we converted that to a z-score. So we used the formula z equals x minus mu over sigma, and that gave us a z-score of 1.89. And then since we're using table A2, or at least that's what I'm using for the video, I'm going to go ahead and erase all this, by the way, just to save some time. Then on the next slide, we can find in table A2 that the cumulative area to the left of z equals 1.89, recall that 1.8 would be the row and 0.09 would be the column, is 0.9706. So then the green shaded area is 1 minus 0.9706. So that's 1 minus the area in table A2, which is 0.0294. So the reason I'm going through this rather quickly is this is technically all review of what I did in my last video. So I'm not going to go through the whole table A2 process because it's just going to take up too much time on this video. Okay, so anyway, we got 0.0294. And as they always say in our book, the result from technology is generally more accurate. But on your homework quizzes and exam, my math lab has a little bit of room for error. And it will still give you full credit if you use table A2, even if your answer is a little bit off from what a computer would figure out. Okay, now the interesting part that we need to learn about today is the answer to part B. So let's go back to the slide where we saw part B. So in part B, they want us to find the probability that 126 main cabin seats are all occupied by males with a mean hip width greater than the seat width of 16.0 inches. So when you first read this, you might be wondering, I mean, how is this any different from part A? So what's different here, and the word that really should give us the clue as to what's going on, is they're talking about the mean hip width. So here, when they say mean, they actually mean the sample mean. So that's actually going to be x bar. Okay, so this is x bar. So because they're asking us about the mean hip width, they're talking about x bar. That means we have to use the central limit theorem, which is the new formula we learned in this section. Okay, so how does the new formula go? Well, it's identical to the other z-score formula. It's just we have to divide by the square root of n in our denominator. Okay, so n is going to be 126. So we can see here that since there are 126 main cabin seats, that's going to represent n, which is the number of data values, really. And we can clearly see that n is greater than 30, so we are allowed to use the central limit theorem. So the way this looks is, once again, they're using greater than. So because they're saying greater than, but they're talking about the mean, we want to find the probability that x bar is greater than 16.0. So this is part B. The only difference is here we're talking about x bar instead of x. In part A, we were talking about an individual adult male. In part B, we're talking about 126 adult males, and we're talking about their sample mean hip width. Okay, so that's why we're using x bar, which represents the sample mean. But we're still going to be using the central limit theorem. Okay, so the formula for that is identical to the z-score formula we've used before. It's just that we divide by the square root of 126. Okay, so we're going to be doing z equals x bar minus mu all over sigma over the square root of n. So notice that the only difference here is now we have x bar instead of x, and instead of just sigma in the denominator, we also have divided by the square root of n. Okay, but here x bar is going to be 16.0. Okay, so using this formula, we're going to have 16.0 minus mu. So this is minus the same mu that we had before. Over sigma, same sigma we had before. And then square root of n, so divided by the square root of n is going to be the square root of 126. So I need to go back to the slides real quick because I forgot mu and sigma. I don't have a photographic memory or anything. So we said that the mean mu was 14.3. And then the standard deviation sigma was 0.9. Okay, so I'm going to go ahead and write those in. And then go back to our camera. Okay, so even though we're estimating x bar, well, we're not estimating, but we're finding areas involving the sample mean x bar, we're still using this number here. So we're still using 16.0. It's just because we're talking about x bar, this extra square root of n shows up down here. So the question is, how do we enter all this into the calculator? And the answer is there are a lot of different ways of doing it. One way you can do it is to just flip this fraction over on the bottom and move the square root of 126 up here. That's one way of doing it. Another way is if your calculator has parentheses, you may be able to actually just type all this in at once. So if you put parentheses around the numerator and then put parentheses around 0.9 divided by square root of 126. As long as you do those parentheses, most calculators should calculate the z-score correctly. So that's how I'm going to do it on mine. So parentheses 16.0 minus 14.3, end parentheses, and then I press the division symbol, and then parentheses 0.9 divided by square root of 126. Okay. And then close parentheses. So interestingly, this gives me a huge z-score. When I get a big z-score like this, it makes me even wonder if I did the problem right. But I got a z-score of 21.20. I rounded to 2 decimal places. So really they're asking us to find the probability that z, because we've converted to a z-score using the Central Limit Theorem, now we're trying to find the probability that z is greater than 21.20. But the techniques that we learned in section 6.2 still hold, and 6.1 for that matter. So remember that greater than goes to the right, and the area to the right, just like on the last example on part A, the area to the right is 1 minus the area in table A2. Okay. Now I did want to, real quick, open up table A2 again, because this is an interesting case. So our z-score is huge here. It's 21.2. And if you don't believe me that that's correct, I can go back to the slides. They have the same number in our book. So well, almost the same number. It looks like they rounded a little bit. So let's see, for their sigma sub x bar, they did 0.9 over the square root of 126. Okay, so 0.9 divided by the square root of 126. So what they did, the reason their number is a little different, or their z-score is a bit different, is they've actually rounded this. So what they did in the book is technically a rounding error. So what I did is actually a bit more accurate. But anyway, if we go to the next slide, they still got a huge z-score. So they got a z-score of 17.00. And honestly, once you get a z-score that's much larger than 3.0 or much smaller than negative 3.0, using table A2 is going to feel a little bit strange. So whether we have 17.00 like they do on the slides because they did a rounding error, or if we have my more accurate value of z equals 21.20, the issue is, how do we look it up in table A2? Well, while I erase this, let's go to table A2. Okay, so in table A2, you're going to notice that a z-score, whether you're using their value of 17.00 or my value of 21.20, you're going to notice that on the left side where it says z, these z-scores, for positive z-scores, don't even go above 3.50. So it says 3.50 and up, then they want us to use 0.9999. Okay? So that's part of the reason why the book can get away with using with rounding in the middle like that. So even though their z-score is less accurate than the one that we got, we're still going to be using 0.9999 as our area from table A2. right? And then just so you know, for your homework, if you have a z-score that is smaller than negative 3.50, you're going to be using an area of 0.0001. So you may or may not see that at some point. But if you do in your homework, or if you have to do statistics in the real world at some point, it's good to know that people will generally approximate as either a very small area if your z-score is below negative 3.50, or a very large area close to 1 if your z-score is 3.50 or higher. So here what we're going to use is 0.9999. Okay, so returning to the slides, or rather the camera is what I meant to return to, and then we'll look at the slides. The area to the right is 1 minus the area in table A2, and we just found that the area in table A2 that we're supposed to use for large z-scores is just 0.9999. Okay, but 1 minus 0.9999 gives us the area to the right, which we're approximating as 0.0001. Actually, with such a large z-score, it's probably quite a bit smaller than this, but because we're using the table, and we're supposed to round areas to 4 decimal places, this is going to have to do. Okay, but if we look at the slides, you're going to see that they did the same stuff that we did. If you're using table A2, the area to the right is 1 minus 0.9999. And as they point out here, it is highly unlikely that the 126 adult males will have an average or mean hip width greater than 16.0 inches. So you can always convert this to a percentage. If you look at that number, the decimal that we got, remember that's the area to the right, but it's also a probability. So you can think of that as, if we move the decimal 2 places to the right, there's a 0.01% chance. So that's a very low chance. Very low chance of that occurring. Okay, and then if we go back to the slides to part C, they have some interesting things to say about it in our book. So in part C, for the design of aircraft seats, which is more relevant? The result from part A or the result from part B? And then they ask why. What do the results suggest about the reduction of the seat width to 16.0 inches? Okay, so let's skip to how they answered it. The book actually has a very detailed answer. So the book's interpretation is the result from part A is more relevant for the design of the aircraft seats. Why is that true? Well, they make the argument that individual seats will be occupied by individual passengers, not groups of passengers. Which is, I suppose, a valid point. I mean, you're not going to have 126 guys sitting on the same seat, or at least that's the argument they're making. So the result from part A shows that with a 0.0295 probability, they might have gotten a slightly different number than we did because they used technology. That's saying that approximately 3% of adult males would have hip widths greater than the seat width. Although 3% appears to be small, that would result in several passengers on every flight that would somehow require special accommodation, and that would likely lead to significant challenges for passengers and the flight crew. Wow, our book really has this all thought out. So the reduction of the seat width to 16.0 inches does not appear to be feasible. So they wrote a full paragraph about this. Feasible just means useful, or doable rather. So basically they're just saying that because even though it's small, 3% of the passengers wouldn't be able to fit into the seats. That would be a huge problem, because what are they going to do? They have to fly, and they can't fit in the seats because their hips are too large for the seats. Anyway, your homework doesn't require a huge paragraph like that as the answer. Okay, but that's good stuff, and honestly, the book makes this section seem more complicated than it needs to be. I think you're going to find your assignments on MyMathLab to not be too bad. Just remember that you have to read whether it's an individual or a mean. And then if it's individual, you use the standard z-score formula, whereas if it's a sample mean, you use the new formula. So x bar minus mu over sigma over the square root of n. Okay, thank you for watching. I will see you in the next video.